Welcome to Part 7 in the module on Patterns and Frameworks for Concurrency and Synchronization. In previous parts of this module, we described the active object pattern and illustrated ways in which you can implement active object using the ACE task framework, and then applied the ACE task framework to implement a thread per connection concurrency model implementation of the JAWS web server. We then moved on and talked about the half-sync, half-async pattern and illustrated how that pattern can be implemented using some of the frameworks in ACE as well. What we then did is we described the monitor object pattern and talked about how we could use monitor object to apply it to a portion of the half-sync, half-async solution in order to implement a synchronized request queue. What we're going to do in this part of the module is we're going to explore how we might apply monitor object along with a number of other synchronization patterns to implement the ACE message queue class and use this in order to flesh out a bit more of our pattern language relating to scalability in a multi-threaded or multi-core environment. Let's first start by talking a bit more about what we need to have an ACE message queue class for in the first place. So it turns out when producer and consumer threads interact with each other in concurrent programs, there's often a need to be able to exchange messages within a process address space. Typically, a producer task will create messages and then insert them or pass them off to consumer tasks, and those consumer tasks will then either process them immediately or more likely do a little bit of processing or no processing at all, and then stick those messages onto a thread-safe message queue. If the queue is full, then the producers typically wait. Either they block indefinitely or they block for a certain timeout period. And likewise, if the message queue is empty, then the consumer thread or threads will either block indefinitely or block for some bounded amount of time, waiting to see if there's some more work showing up for them. So that's kind of the background of why you need an ACE message queue and sort of how it interacts with other pieces in the system. When we implement ACE message queue, there's a number of pieces that it involves. One piece is the message itself, and we call this the ACE message block. The purpose of the ACE message block is to be able to manage the memory of the message in a very efficient way, allowing us to do a couple of things. First, it allows us to be able to support reference counting. So if we end up having to use a message that's held from a couple of different parts of our solution, say in a retransmit buffer, we can do reference counting to be able to make a logical copy of the message without having to physically copy the data itself. So that's much more efficient. Another thing you can do with an ACE message block is you can also chain together a sequence of ACE message blocks to form some kind of composite message, which can be useful in situations where you're dealing with a lot of network protocol messages, where you have to add headers and trailers to them. And you want to be able to do this again without having to copy the messages repeatedly. Another thing you can do with an ACE message block is it's got next and previous pointers, and so you can actually chain together groups of ACE message blocks, which themselves may be composite messages, in order to be able to provide a doubly linked list that we'll use for the ACE message queue that we'll talk about in just a moment. Another thing you can do with an ACE message block is you can treat synchronization and memory management issues as aspects, and you can change the locks. You can change where the memory comes from without changing the logic of the class itself. This composite structure, as a general rule, is intended to minimize data copying. So you can often get by without having to do a full copy of the data, and you only have to update reference counts in various ways. This particular abstraction handles the variability of messaging operations via a common interface. An ACE message queue is really nothing more than a doubly linked list of ACE message blocks with a number of other mechanisms thrown in for good measure in order to be able to make it easier to work with this as a cohesive abstraction. For example, there are operations on an ACE message queue to be able to enqueue and dequeue messages at the head or the tail. And you can also go ahead and enqueue messages in so-called priority order, such that when you dequeue them, the message of highest priority is always the one that will be at the front of the queue. Something else you can do with an ACE message queue, and it depends a bit on the synchronization properties we're about to talk about, is you can also do timed operations. If the queue is full, for example, you can have it block until the queue is no longer full. Now, this concept of being able to block or not depends on something called the synchronization strategy that is configured into the ACE message queue. And this is again done as an aspect using the strategy pattern and using C++ templates. And so as we'll see, and this will cover actually the bulk of the discussion throughout this part of the module, we can embody or configure an ACE message queue in a couple of different configurations. One configuration is single-threaded, which means that it never blocks, it just fails if it's empty or full. Another configuration is multi-threaded, to use a multi-threaded synchronization strategy. This is the way we would typically do it, of course, when we implement the half-sync, half-async pattern, and we need to have a synchronized request queue. In this case, it'll end up being able to block under certain circumstances, which we'll talk about in just a moment. Some other things you can do with a message queue: you can control its synchronization strategy. You can also control where its memory allocation comes from. So it can come from different allocators that may be allocated out of different types of pools of memory. What this particular class does from a commonality and variability point of view is it handles the variability of queuing and synchronization mechanisms of queuing behind a common interface. And we'll talk about why we do this as we go throughout this part of the module. So let's first start talking about this notion of being able to transparently parameterize synchronization into a class like ACE message queue. The various concurrency patterns we've talked about before give you a hint here that you might want to keep certain components fixed with respect to their functional behavior, but be able to change their synchronization strategies depending on how it is they're being used. So it might turn out in some situations we just need to have a queue to store data, but we don't need to have that be synchronized or thread safe. Conversely, when we start trying to work with the half-sync, half-async pattern, we need to have a synchronized request queue. Well, you can imagine doing things in a couple of inadequate ways or dysfunctional ways. One approach would be to try to maintain multiple copies of queues that were customized and hard-coded for different synchronization use cases. For example, we might have a non-synchronized message queue that has no locks in it whatsoever. Conversely, we might have a synchronized message queue that has a bunch of locks in it. Well, the problem when you start trying to do this is now you have to manage these different variants manually. And that means that when you make changes in one, you have to make sure you go make changes in the other. As you add new features, you have to make sure those are added. As you fix bugs, you have to go and fix them in multiple places. And that quickly becomes unwieldy. What's a more effective approach? Apply the strategized locking pattern. This pattern is a pattern that appears in the POSA 2 book, and I'll give you a link to a paper where it appears as well. And basically what it does is it allows you to treat synchronization as a first-class citizen from an aspect perspective. And you can strategize different synchronization mechanisms via a common interface. So we can use that to keep, say, ACE message queue fixed and then change its synchronization properties without changing its other parts of its implementation. Take a look at this URL for more information about this particular pattern, which again appears in the POSA 2 book as well. Here's a way to apply this particular pattern to ACE message queue. We follow a couple of steps here. The first step is to strategize the locking mechanisms. So if you take a look at this particular class, which is a snippet from the ACE message queue class, what it does is it makes the synchronization strategy a template, and then we can use various traits from the template parameter that's passed in order to get the appropriate kind of synchronization strategy that we want with respect to mutual exclusion, as well as various condition operations for the not empty and not full conditions. Here's an example of how to define some of the different trait classes we might have. You'll notice here that we have 2 trait classes that are built in from scratch. You're welcome to add more, of course, because it's extensible. One model is the ACE null sync class, and this has nothing but a bunch of no-op traits that do nothing. They're the null mutex, the null condition, the null semaphore, using the null object pattern. The ACE empty sync, in contrast, that particular traits class, has real synchronizers. It uses ACE thread mutex, ACE condition. It uses ACE thread semaphore, and so on. And each of these provides real mechanisms that can be used in a threaded environment in order to work appropriately to lock and wait and notify when things change that are important. Notice by using traits classes that it doesn't require us to have any common base class or even use any virtual methods at all. We can simply use the magic of C++'s signature-based type conformance and the template policy mechanisms in order to parameterize the way in which we use these with ACE message queue. Speaking of which, let's take a look now at how we could use these trait classes to instantiate the appropriate variant of ACE message queue depending on what it is we're trying to do. If we don't need synchronization at all, we can simply provide a no-op synchronizer like ACE null sync and that traits class. And that means anytime you try to dequeue from a queue that's empty, it won't block. It'll just fail. Conversely, if we apply the ACE empty sync traits class to make a message queue, and we define an instance of one of those types of synchronized objects, then when you do a dequeue head on an empty queue, that will block until somebody puts something into the queue to allow it to be able to continue. So the nice thing here is the logic remains the same, but we're changing the synchronization mechanisms via the strategy and the strategized locking pattern. I show an example here that's using templates and basically static typing and early binding. It's also common practice to use some kind of base class with a common method with virtual methods in order to be able to plug these things in at runtime as well. The benefits with the template approach, there's less overhead. The downside, it's less flexible. The benefits with the virtual methods and inheritance approach is it's more flexible at runtime, but there's a bit more overhead. Whether that overhead matters for you, of course, is up to your profiling and architects to decide. So let's talk about some of the pros and cons of strategized locking. The benefits is it enhances flexibility and customization. You can change the different locking mechanisms very flexibly without having to modify the behavior of your class. That means you have less work to maintain different variants because they all exist in one place and you just strategize locking. You can think of this as a glorified example of the strategy pattern applied to the context of synchronization. It also, to some extent, can improve reuse because now you can have these reusable components that can be strategized for different use cases in different contexts. And it's a very simple thing to do. Of course, there are some downsides. One of the problems is that the locking now moves out to the interface of the class. And sometimes you want the locking mechanisms to be secret, so people don't even know that they exist. And this makes them more overt, more obtrusive. You might also think of this as being a bit over-engineered. If you're not careful, people can do it wrong. They can put in the wrong kind of locks, and things will fail in somewhat subtle and pernicious ways. We'll talk about a couple of other patterns shortly to help reduce the risk of that occurring, but it's always a risk. So that was basically the strategized locking pattern and applying it to the ACE message queue. Let's now talk about another dimension of synchronization that corresponds to what we just described. This is ensuring that locks are released properly. If you start writing single-threaded code, then releasing locks is a non-issue. When you begin to write multi-threaded code, of course, releasing locks is a big deal. And if you don't release locks properly, you can end up with deadlock or other kinds of inefficiencies in your solution. This is a particularly tricky thing when we start trying to apply things like strategized locking, where it's not always clear whether we're locking things for real or not, because we might have null locks or recursive locks or non-recursive locks and so on. But in any case, we have to write the code that acquires a lock on the entry to a critical section and releases it on the way out. And if we're not careful and we write the code like is shown on this slide, some bad things can happen. In particular, if something goes amiss in the implementation of this method is the dequeue head method, then we might not actually release the lock on all exit paths out of this method. For example, if it does a return, that lock might not be released. If an exception is thrown, the lock might not be released, and so on and so forth. If a goto or a break statement is called, for example, the lock might not be released. So how can we ensure that these locks are always released properly? Well, we're going to apply the scoped locking pattern. And this pattern will make it possible to use some features of object-oriented languages where constructors acquire resources and destructors release them to ensure that the scope over which things are applied will always properly acquire and release the locks automatically. You can take a look at this particular paper for more information about this pattern. So let's talk about how we might apply scoped locking to the ACE message queue implementation. What we're going to do is we're going to define a guard class. This particular one happens to be part of ACE, but you could do the same thing if you didn't use ACE. And this guard class, which is a template class, follows a very simple protocol. Its constructor is going to acquire a lock that corresponds to the parameter that was passed into the template, and its destructor is going to release that lock. So when we come in, the constructor acquires the lock, and the destructor releases the lock, thereby ensuring that we always are going to release the lock, whether or not we have an exception or a return or a goto or anything else that will allow that scope to be exited. The ace guard that we show here as a helper class also illustrates another reason why wrapper facades are so powerful. Notice that we're using the wrapper facade mechanisms for ace thread mutex, ace semaphore, ace reader-writer locks, and so on. And all of those have the same interface. They all have acquire and release methods. And so all we have to be able to do to use all these different mechanisms is create a parameterized guard class, which is a helper class, that implements the scoped locking pattern, and then we can parameterize it with a particular type of the wrapper facade. If you were just using functions, it would be much more complicated to work this way. So once again, wrapper facades provide building blocks for more powerful composition and capabilities with object-oriented designs. The next thing we do is we let the critical sections correspond to the scope and lifetime of these guard objects. Here's an illustration using the DQ head method that we had in the message queue from before. Now what we do when we come in is we use the scope locking pattern in order to be able to automatically acquire the lock in its constructor. And then no matter how we leave the scope, short of crashing the program, that lock is going to automatically be released, which is much more powerful and much more foolproof. You're not going to make as many mistakes because it automatically cleans things up. You can allocate instances of the ace guard on the stack, so they're very lightweight, they don't require any dynamic memory allocation, and they just grab the lock on entry and release the lock on exit to a scope. There's a number of benefits, of course, to using this particular pattern. It makes things more robust because you can eliminate this common source of overheads where you have the mistake of forgetting to release the locks or jumping out of the scope too quickly and having problems. This, of course, is really an embodiment of a broader C++ idiom called Resource Acquisition is Initialization, or RAII. And you can read more about RAII here at the Wikipedia site. There are some limitations with using this particular pattern. One of the problems is that you can end up with deadlock if you use this recursively. We'll talk a bit more about how to get around this particular problem, but if you have self-recursive calls, you can end up with deadlock on a non-recursive mutex, which could be a problem. And there's also some language semantics issues. We're using C++ programming language features, and while that will work for certain things, it doesn't know about low-level features that are available in the operating system to do things like exit threads by thread exit calls, or do long jumps using set jump and long jump mechanisms. So if you're not careful, you could still find some way to subvert the ability to release the locks automatically. But at least this gives you a fighting chance for the common case. The next and last part of this particular part of the module will describe one of the consequences of applying the strategized locking pattern. If you think about strategized locking, it was encouraging you to make the locking mechanism a policy or a strategy that you could parameterize with your components. So for example, now we have an ACE message queue where we can parameterize the particular type of locking mechanisms that we use, the strategy for that. The tricky part here is if you have abstractions, classes like ACE message queue that have intra-object method calls, you have to watch out for two things. The first thing you need to watch out for is not incurring unnecessary sources of locking that aren't strictly necessary or needed. And the second problem you have to watch out for is ending up with self-deadlock. So let's take a look and see how this might arise. So here we have an example where we've got the DQ head method, and depending on the type of lock that's strategized into the ACE message queue, you're either going to have extra overhead in this example, or you'll have self-deadlock. Why is this? Well, the reason this is the case is because the DQ head method in this implementation first acquires the lock using the guard, and then it calls isEmpty to check to see whether or not the queue is empty or not. IsEmpty, as you can see, is an interface method that also acquires the lock, and then it goes to check to see if there's any bytes in the queue. Well, the problem there is if we give this thing a non-recursive mutex, it will self-deadlock. And even if we give it a recursive mutex, we'll still have an extra level of locking that really isn't strictly necessary, which increases the overhead. So how can we avoid this particular problem? Well, we'll apply another pattern. This is called the thread-safe interface pattern. And this pattern is used to minimize unnecessary locking and ensure that intra-component or object method calls don't end up incurring self-deadlock. So let's talk a little bit about how this pattern works. What it does is it splits the world up into two parts. It has interface methods that check and do very little work, and it has implementation methods that trust and do work. And implementation methods only call other implementation methods. By organizing things this way, we can have the interface methods acquire the locks and then call down to implementation methods to do the actual heavy lifting and do the actual logic. Those implementation methods assume, trust, the locks are held, they do the work, and they only ever call other implementation methods. This pattern also appears in POSA 2, and you can read more about it at the URL at the bottom of this particular slide. Let's see how we can refactor our code to apply thread-safe interface to ACE message queue. What we can do in this case is we can split things up a little bit. Instead of having the DQHead method call isEmpty, which is an interface method, instead it acquires the lock, and then it calls down to the isEmptyI method. IsEmptyI is the implementation method. As you can see, isEmptyI is a private method. It's not public. It trusts that it was called in a context where the lock was properly held, and it actually does some work. In this particular case, it just checks to see whether some counts or 0 and doesn't do any other work. But if it was actually doing some other work, it would only be able to call other implementation methods, not call out to the interface methods. This pattern, as you can see, allows a broader range of synchronization strategies to be used without running afoul of those issues of self-deadlock and additional overhead. So to talk about some of the benefits and limitations of this pattern, the key benefit, of course, is increased robustness. We can avoid having to worry about this self-deadlock issue. We avoid extra calls that are going to be unnecessary and cause additional locks, even if it's going to work with the use of recursive locks. We may be able to enhance performance by doing that, and we can simplify the software by decoupling out the locking logic from the business logic. And that may have some other benefits as well by being able to think more clearly about what your business logic is. Naturally, there are some downsides, as always. There's additional indirection, and there's lots of extra methods. For every interface method that matters, you may also have a corresponding set of implementation methods. So that means your surface area of your class will go up, even though the public interface may remain the same. There's also, of course, the potential for misuse. In some object-oriented languages like C++ and Java, they have class-level access control as opposed to object-level access control. So it's potentially possible to peek around and access things you're not supposed to in those environments. So you have to be careful how you use this pattern. You have to check and ensure that people are not violating the rules in any malicious or accidental way. So this particular set of patterns has helped to explain ways in which we can take what ACE message queue provides us with respect to a queuing mechanism and then use the monitor object in conjunction with strategized locking, scoped locking, and thread-safe interface to make the ACE message queue much more reusable, much more flexible, much more configurable for a wide range of contexts in which we're likely to use it, including, of course, for our half-sync, half-async implementation that we use for the JAWS web server.